Good afternoon. Thank you very much for joining us. I hope the lunch was good. Yeah? Yeah? Did anybody eat any crembo? No? Okay. I was told if I do a good job, I will get 2 crembo today. So hopefully you have a chance to see the demonstrations here. It's a good opportunity to not only see the presentations, but get some hands-on experience with some of the test and measurement equipment. This is always part of an engineer's training, besides the theory and the practical. The hands-on is, of course, very important. So I encourage you all to get in there and ask lots of questions for what we have from all of the test and measurement companies here. So today I'm going to talk about a new method for PCB insertion loss characterization. And I've used this presentation earlier this week, so I apologize if some of you have already seen this. I'll try to change it up a little bit to make it a little bit more interesting. And I certainly don't mind any questions. I don't know what the format is today. If you would rather save the questions to the end, that's okay with me too. But as you can see, we've got a lot of different challenges in our high-speed digital design. And whether we're doing linear passive interconnect or SerDes chipsets or time domain measurements, frequency domain measurements, all of these things play into a tool set for design engineers. So today I'd like to talk about this method of characterizing the excuse me, I've got to get used to this. This is another tool that engineers have to learn how to use. And we're going to talk about this method of PCB insertion loss, some of the traditional methods. So it helps to know what the traditional ways of doing things for many years in the past, and learning how the improvements make our lives easier and more efficient, and hopefully more accurate. This is our goal as engineers. And then we'll do some comparisons. We actually had, there's quite a bit of data in here, so I don't want to dwell too much on the data, but it's interesting to look at some of the comparisons. So this is something I think is worthwhile to spend some time on. And of course, simulation is something that we all should be familiar with. I'm a digital design engineer by education. I took one course in field and wave theory in college, and I said, forget it, I'm going digital. Well, of course, today, the high-speed digital signals have such fast rise times. Everything on PCB traces are microwave transmission lines. So we must learn some of these tools, and SParameters go along with this. And simulation, of course, is part of correlation to measurements that we must do together. And we have a couple different reference devices that we measured that we'd like to compare. Certainly, if you have a method that you're trying to authenticate, you would like it to be useful for many different types of structures. And then, of course, there are some considerations in the algorithm itself. Some of you may have seen this slide before, but I'd like to use this as a model just to give you an idea of how to think about the different types of error correction, because a lot of us use terminology that may be the same or may not be the same. And if we all speak the same language, this helps communication. In terms of error correction as a general field, we like to categorize 2 main types of error correction: pre-measurement error correction and post-measurement error correction. So pre-measurement error correction are these with the circles, and this typically is what we call calibration, yes? So before the measurement's made, we calibrate. So short open load through is probably the most common type of calibration, especially on a vector network analyzer, but also on a TDR, a time domain reflectometer, which is basically a time domain instrument. Then all of the post-measurement error correction, SParameter de-embedding, port extension, time domain gating, these are done after the measurement is made, and usually people will call this de-embedding as a general term. And this is fine, but one thing we want to make sure we clarify amongst our engineering community, our colleagues, whether it's in our own group, our customers, or our vendors. When we talk about de-embedding, that means we have the S parameters, or the touchstone model, of the structure that we want to de-embed. Okay? If you do some type of error correction after the measurement, but you don't have the full S parameters, that's okay. But I wouldn't call that de-embedding. I would call it some other type of correction, either port extension, time domain gating. And just because something may be a little less accurate doesn't mean it's bad, okay? Everything is a tool. If we're going to do something and we just need a fast, easy, quick answer, time domain gating, port extension is perfectly fine. But if you're going to do publishing or you're making big decisions upon data sets, then I would feel personally more comfortable with S-parameter gating, or excuse me, S-parameter de-embedding. Okay? So as you can see, most of this is a linear type of relationship between accuracy and simplicity. And this is very intuitive, right? The more time you spend and the more details you pay attention to, the more accurate it's going to be. Something new that has come up in the past couple years has been something called Automatic Fixture Removal, or AFR. And this is something new that we think has both accuracy and simplicity. And so a lot of standards committees are looking at this now, and so we're in the process of using this more, but like anything else, it's just a tool. So with printed circuit board insertion loss, why do we need to measure this? Why is it important? Well, we have to extract electrical parameters of devices. We need to look at PCB performance. Of course, the passive channel, this is where most of the action happens in between a transmitter receiver. You can get the fastest chipset from TSMC or any manufacturer in the world, but if your passive channel is not designed well, you will not take advantage of that fast chipset. So it's the whole ecosystem that you must be concerned with. And don't leave the passive interconnect to the last point just because it seems to be the simplest. It's an integral part of the whole channel. And of course, PCB materials is a very big issue. FR4, sometimes we basically are, I don't know how else to say it, but maybe doomed to use FR4 much more than we want to. It's a very inexpensive material, but it's something that has to be used in order to reach a lot of consumer applications. And so what we want to do as engineers is step up to that challenge and do the best we can to get just as fast a data rate through this material that is really not forgiving. And of course, the fabrication process of the PCBs is related to what type of insertion loss you'll end up getting in the channel. So what are some of the traditional methods that have been used in the past 10 or 20 years? Well, the first direct loss subtraction. This is one type of methodology where you have a device, for example, like this, where you have a differential transmission line of length L that seems to be well balanced, and you have some type of launch on either side that we might call the test fixture, input and output test fixture. And this right here could be the test fixture that you use to subtract from the complete channel. And what the result would be is the delta L. Okay, so this is just a very straightforward, rudimentary direct subtraction that we'll talk about a little bit more. Then TRL through reflect line. Maybe just for curiosity, if I could ask for a show of hands, how many people know what TRL calibration is? Just a show of hands? Okay, okay, good. This is something that the microwave engineering world has used for 20 years that has been focused on vector network analyzer testing and RF circuits, okay? And a lot of times we adopt engineering processes from different fields, and this is one that we as digital design engineers have tried to adopt over time, and there's been various success with this type of methodology because of the cal kit that needs to be created. And so I'm going to talk a little bit about that and the challenges and how we overcome those. And then automatic fixture removal with 2x through. This is a similar channel with the 2x through fixture, but there's a little bit different mathematics that are employed here. So these are the three methods that historically people have used. Now, direct loss subtraction, you know, you can use this with measuring the full channel and the through fixture here, and when you subtract one from the other, you get a fairly reasonable result. But the point is that you're not exactly doing a de-embedding with S-parameters. So an S-parameter is a behavioral model that gives you all the reflection and transmission terms throughout the frequency band of interest. The limitations here is that the two lines must be consistent from the one side of the differential pair to the other. Then also the line characteristics, which, how do we define a transmission line? Well, if it's a single-ended line, there's only two parameters you need. This is propagation delay and impedance. However, with the differential pair, the resistance or impedance is not a simple number, it's a matrix. Okay, so things get a little bit more complicated with differential, but out of all the three methods, this is probably the simplest to use. But it does have limitations. Now, the TRL is traditional and has been used for quite a long time using the flow graph. And the flow graph gives you the terms that you need in order to do a full error correction. And the error correction inside the test equipment for a VNA has couplers and switches that are very high frequency that need to be operating in both directions, transmission and reflection, very accurately. And so the TRL has been very good for microwave world because the dielectric materials have been very consistent, shall we say. Ceramic or LTCC, there's other types of packaging, and there's only one net typically on a microwave circuit. However, high-speed digital, we have the double whammy where you have both many channels and a poor dielectric. And so fabricating this TRL cal kit down here requires very careful methodology, and it's subject to error because, let's face it, PCB fabrication is not really all that high tech. And FR4, how many people know what FR stands for? Fire resistant. So they didn't really design this stuff to perform high bandwidth, but they just wanted it not to burn up or smoke. So this is part of our challenge, though, because we need to keep costs low. Now, with the TRL cal kit, TRL through reflect line, those are three standards that need to be designed and fabricated. And the L, there's usually more than one line 1, line 2, line 3, of different lengths that correspond to different frequency bands over which you're removing the test fixture, making the measurement. And so, so this is, honestly, I mean, I know that there's probably 10 or 20 companies that are very good at this on PCB, but it's not easy. And it's usually not something you get right on the first board turn. Now, automatic fixture removal, this methodology requires 2 SParameter measurements, and it will be measuring the full channel with the fixture input, fixture output, and the device under test, and then something called the 2x through, which is just the launch on either side. As an example, I have a backplane here, and you can see where, as an example, you can think of your own specific device under test. It may not be a backplane, it may be a cable, but in some fashion, you're probably going to end up with a very custom connector, like a high-speed HMZD backplane connector, for example, on this Tyco backplane. And these connectors don't directly attach to any type of instrument, whether it's a VNA or a TDR. So getting the S parameters of the fixture is complicated. Historically, what's been done is you would send this fixture to a third-party company that's really good at probing and making measurements, and they'll rip off this HMZD connector, so you've got empty vias that they need to clean up, and they'll probe that side with the vias, and they have to do a mixed calibration system where the probes will touch down on a ISS calibration substrate, short, open, load, through, and then they'll do an SMA calibration on the other side of the fixture, and this will allow them to make a S parameter measurement and then de-embed the test fixture. And you know, a month later, $10,000 later, you get a messed up board and you get the model. So there's got to be a better way to do this. Rather than letting other people fish for you, why don't you learn how to fish? So this is kind of the idea behind the AFR. What the 2x through methodology is basically, instead of TRL where you build 5 different calibration structures, here you build one. And the one is a 2x through, but you have to build it on a separate card, or you have to build a separate structure with no connector in the middle. And the idea is that you want to have this launch be the same as this launch. And this is not easy because there's excess capacitance, excess inductance right at that coaxial to planar transition that's very difficult to control, both EMI-wise and electrically. But it's much better than building 5 standards through reflect line 1, line 2, line 3. Okay? Now, limitations. Everything has limitations. We need to understand what they are. Here, the launches of the 2x through must be consistent with that of the longer line. So again, these launches have to be the same here and here. SMA connectors must be the same. The 2x through and longer line need to be symmetrical top to bottom. So we hope there's not much mode conversion. We'd like to have a well-designed differential line, well balanced. The return loss and insertion loss of the 2x through cannot cross each other in the measurement frequency range, often at least 5 dB separation. Okay, I want to talk about that last limitation a little bit. So sometimes, once a month minimum, I'll get a call, Mike, this AFR is not working, fix it. And I'll say, well, send me the data, send me those 2 S parameter files. Just email me the complete channel with the fixtures and the DUT, and send me the file with the 2x through, and we'll see what's going wrong. And half of the time, it's due to the fact that the test fixture has insertion loss and return loss that cross. Not only do they come close, but they cross. And this is just the indication of a poorly designed test fixture. So what happens, sometimes I can understand the point. I've got a 25 gauge gigabit device under test. This backplane that I need to test has to work at 25 gigabit. But the fixtures, I'm going to spend an hour designing them, and maybe they'll go to 5 or 10 gigabits, and I'm just going to de-embed those anyway. I don't really need to care much about them because I'm taking them out of the measurement. Wrong. You need to spend as much time with the test fixture design as you do the actual device under test. You can't take a poorly designed test fixture, de-embed it, and expect to get high frequency performance measurements. Okay? So this is kind of it may not be intuitive at first, but once you realize it, you can do a design that works well. So the rule of thumb here is spend as much time designing the fixtures as you do the device under test. And it'll help you down the road when you're doing de-embedding and other types of error correction also. Okay? Is this clear? It should be clear. Okay, so the second generation AFR is probably something that's come around in the last year and a half, maybe 2 years. And the concept here is that I don't need to build a 2x through, but I can use a 1x structure as a calibration point. And I can measure S11, or in this case with the differential structure, SDD11, differential return loss. And from that one measurement, I can extract SDD22, SDD12, and SDD21. So both differential return loss, forward and reverse, differential insertion loss, forward and reverse, and that gives me the full 2x2 matrix that I need to form a model of the test fixture. So let's think about that for a moment. The idea now is I don't even really need to build a 2x through anymore. I can take the fixture and I can pull it out and I can use the open circuit here as the open. So I don't need to measure a through. I don't need to pull this connector off and probe it, nothing like that. So it's just a reflect measurement, which is quite easy. Now, again, there's limitations we need to be aware of. Again, the launches have to be consistent. That's without saying. The impedance variations of the trace must be as small as possible, especially when you're getting close to the open response. And this has to do with controlling the EMI fields at the end of the open. So part of the algorithm is assuming a reflect that does not radiate excessively. Okay, what does that mean? How much is too much? Well, if you have a male SMA type connector, coaxial, with that male pin sticking out, that's a great radiator, a great receiver. So that type of structure will not work with this method. Okay? So how do you know if your custom connector will work well or not? Well, the easiest way is to just try it. And the fact that you don't need to build anything to try it makes it very easy to check. So you make a 2-port SDD11 measurement of whatever structure you have as a test fixture. If the open circuit radiates excessively, you'll see strange data that may become non-causal, which means if you try and put it into a simulation engine, it'll blow up. It'll make perhaps a passive device like a PCB look active or have gain, which is not possible. Strange things like that. So if that's the case with this methodology, the next step is use a short. So somehow, whatever physical geometry of connector you have that's custom, if you can put maybe a loop back or a jumper. Now, of course, there's going to be some loop inductance due to this, and depending upon the spacing, it may be big or may be small. But again, it's a quick reflect measurement that you can make easily and apply in the algorithm to see if it works. Now, what if those two things fail? Then you go back to the first generation AFR, which is the 2x AFR, and with this one structure that you build, there's no concern about radiation of a reflect open circuit. So that's kind of the troubleshooting or process that you would go through if you're thinking about how to optimize de-embedding. So let's get into some of the data. So the first thing that we did was some simulation. So if you have a perfect data set, you kind of know what to expect. And so we built a model in ADS, 11-inch line, various geometries of launch and throughs, and we did simulations of the S-parameters, looked at the loss, and we had a couple different test cases with both 100 ohm and 90 ohm. So we're not always able to enjoy a perfect 100 ohm impedance environment anymore. We have standards that require non-100 ohm environment, and this is something that we need to step up to the challenge. It's not always easy, but there are benefits in the system. So, so this is what the model looked like in ADS. And if you look at the differential insertion loss, and I didn't bring my glasses. Sorry. So in the blue curve, the actual data, and the red curve, which is the 1x AFR, you can see where they lay almost on top of each other, up into 25 gigahertz. And this green line here is just the difference between the two in dB. So we just divided one by the other. And so you can see up to 25 gigahertz, we found that if we knew we needed results up to 20 gig, we would test it up to 25 and then truncate. And so, you know, the idea is that if you have extra bandwidth in your test equipment, this is a good thing, and take advantage of it. So this is the first set of data. Direct subtraction at 100 ohms. You can see that this method, when we put them on a comparison for differential insertion loss, there's more difference. There's ripple at the higher frequencies here. And we found that this was due to the residual mismatch inside the structures. So the direct subtraction was sensitive to this type of mismatch. This is not a good thing for the algorithm. We'd like to have something insensitive to this mismatch. The 2x through, again, the blue is the simulated data. The red is the 2x AFR. We have very good correlation here. The difference in the green line is almost perfectly flat. A thousandth of a dB. Okay, this is quite good match. Up to 810 megahertz. Again, the second generation AFR with the 1x through that uses the open circuit, we found very good correlation with the simulated 100 ohm structure. This was here 800ths of a dB. Okay, so now let's go to the 90 ohm direct subtraction. A little more ripple here. We had almost 0.2 dB. Okay. Again, due to the residual mismatch. 2x through AFR, we had 0.05. And then finally, the 1x AFR, we had 0.08. So if we summarize all of this data into one slide, it'll look like this. And you can see that the direct subtraction is typically the least accurate. The 2x through typically is the most accurate, but then you're building one structure. You still have to go design and fab that 2x through. Maybe that's easy for your company, maybe it's not. Either way. The 1x is easy to try, and when you get down to the details, this is really nothing when you're talking about high-speed digital. So again, the idea is try the 1x AFR method because it's easy and quick to try. So that was comparing everything to simulation. Let's take a look at measurements of different structures. So again, we had three different structures. We had a stub that was in the middle of a 8-layer board, excuse me. We had a back drilled via. Now, we all know why the back drilled vias, right? We know that stubs cause excess capacitance. I mean, characteristic impedance Z0 is equal to square root of L over C, excess inductance over excess capacitance. And so big via stubs, particularly on thick backplanes, will wreak havoc in your high-speed digital channel. And so we want to avoid via stubs. So either back drilling, perhaps micro vias with lasers will work also, or you can route everything on the top layer and the very bottom layer and void stubs altogether. But we usually use that real estate up for high-speed channels very quickly. So we're forced to go inside the layers. So here, these three structures is what we're going to take a look at next. So here are the two test vehicles that we created. And kind of interesting, on this board here, you can see that the transmission lines are off at an angle compared to the edge of the PC board. Why do we do that? Well, there's a weave in the FR4 fiberglass, and if you have one side of the differential pair over epoxy and one side over a weave, you're going to get two different relative dielectric constants and different propagation velocities, which would create skew and potential mode conversion and crosstalk. So that's not a good thing. So this is something that many people do with high-speed channels on FR4. So here we did 100 ohms, layer 4, and we did the comparisons here, and you can see here we're very, even though the direct subtraction is twice these others, it's still extremely low. Layer 4 with the back drilled via, we're still down in this area here, 0.6 dB, but we're 4 times or so better. 100 ohm layer 6, we're still considerably less, under 1/10 of a dB per inch. And now if we look at all three structures overlaid, pretty good correlation. And then again, we're doing the same experiment, design of experiments on 90 ohms. And so for layer 4, the back drilled via, here, it turned out for this type of structure, even the TRL, which is the mainstay of microwave calibration, still had problems. TRL can usually be considered the baseline of what you want to compare to. But even in this case, there's issues because the TRL cal kit was not designed to match the structure exactly for the launches on either side.
For 90 ohm?
Yes. This was 90 ohm. So after kind of sifting through all the data here, I think the summary kind of says it all. Regardless of the impedance environment, whether it's 100 or 90, regardless of the structure, whether it's a back drilled via, a long via, small via, there are a couple different methodologies you can use that are just as accurate as TRL, if not more accurate, but much easier. This is the bottom line point that we were trying to show with the design of experiments. So since TRL is the historical standard, that's kind of what we wanted to compare to. The direct loss subtraction does show ripples at the high frequency, as we saw. The TRL calibration may have big deviation too if you do not properly design that cal kit. The most recent second generation 1X AFR works regardless of the impedance environment and the structure. So in a nutshell, that's the presentation. Thank you. Question here is, so we measured 100 ohm impedance environment and 90 ohm impedance environment. How low of an impedance environment can you use these methods for? We haven't done the experiments, but there's no reason why you couldn't go significantly lower. The caveat is this. If you use a VNA, you can change the port reference impedance with the calibration so that it matches your network. You can have a VNA output impedance of 50 ohms differential or 70 ohms differential if you make that calibration. You just change the center of the Smith chart. A TDR doesn't have as much flexibility, so you're going to live with an initial impedance discontinuity at the very beginning of your device under test, or in this case, your fixture. So if you launch a 35 picosecond rise time, 200 millivolt TDR step into one of these channels, and it's differential 70 ohms, you're going to lose a lot of energy, and at the end of the channel, depending upon how long it is and how lossy the material is, you're going to have maybe very small signal that may be difficult to pull out of the noise because of the wide bandwidth TDR receiver. That's kind of a generalized answer, but that's what will happen. This gentleman has an application very similar to the device I showed with 2 daughter cards in a backplane, and he's measuring insertion loss, but he wants to measure it in a vibration chamber. The first thing I would say is don't put the test equipment inside the vibration chamber.
Is the wire long enough in order to get it from outside to inside?
What's going to happen is microphonics, which is mechanically induced noise, electrical noise, is going to start to swamp out your signal. You're going to have some vibration isolation between the test equipment and the device under test. And anytime you have cables shaking,
no, I have damper on the cable. There is a pipe, the wires are going through the pipe, and
okay.
I have damping around the damping material between the pipe,
okay.
periphery, and the wire itself.
Okay, so if there's dampening material and you minimize the microphonics of the test cable, I think that you would probably get reasonable data up to some frequency around 20 gigahertz. I wouldn't really trust it above 20 gigahertz. I would have to be a bit skeptical. But you can calibrate without vibration. So if you calibrate without vibration, you set a very good reference plane right up to the input of your DUT. So turn vibration off, calibrate, turn it on, hope the dampening is okay, measure up to 20 gigahertz. Okay? Very good. Okay, we'll be around here later today if you have more questions. Thank you very much.